Right, can you hear me? Yay! Right, we are going to overrun because the 44con guys have decided to take up 20 minutes of our talk. So because of the history of the Nerf gun, we decided to go out and buy a Nerf tank because why not? Next slide, please. So why are we doing this? Because it's interesting, it's fun, it's different from a normal device. Unlike most things, it doesn't use Wi-Fi or Bluetooth. It uses a generic 2.4 gig radio. Forgotten the word. 2.4 gig frequency. That means there is a problem here. Our demos may or may not work because it's 2.4 gig, which is the same as wireless, same as Bluetooth. Okay? Just a wee bit of a warning first. So that means Steve may get away with this temporarily. So also, it's a friggin' Nerf tank. How cool is that? So next slide. Yeah, I know. So we decided that we needed a plan here, and we have our effective blueprint designed by our marketing manager. He's great with graphics. So what we needed to do was get a tank, followed by we need to hack the tank, drive it around 44con, which you may have seen Ken do that earlier, and finally, gun him down. That's you, Stephen. So we started this by the obvious way. It uses, RF, raw RF, not Wi-Fi or Bluetooth. So we need to have a look at it. So the problem is at the time we restricted ourselves because we could only get one device. We couldn't take it apart. Ken explicitly said what would happen if we took it apart. And I can't really say that in a public arena. So can we reverse it from the air? For this, we needed a plan. Get used to this, there's a few more. This is where our marketing manager didn't read the brief properly, and yes, I know that for the pedantic, that's a hack RF, not a USRP. So we use a USRP, which is a generic sniffer of radio waves that we can use. We sniff our communications, and we profit. Well, take control of the tank. So, and then we did this, we sniffed it, and I've got a little admittance to make. We didn't actually take a screenshot. So I stole that from Google Images about an hour ago. But anyway, after we sniffed, we sort of, a discussion between Chris and I happened. It was sort of like this. Yep, that's a signal. And Chris sort of said,
yep, it's a signal.
So essentially, this was, it was basically not getting us anywhere, and it wasn't getting us fast. We waited the whole morning, so we came up with this cunning plan. We knew Ken had to go off and talk about kettles. So we have a plan.
So the first part of the plan was wait for Ken to leave the building. Second part was take it to pieces. Third part, solder things to it so it'll never work again. And fourth, profit. And Dave can show the result.
I've got a controller here, and as you can see, it's easy to fall apart. There was actually a joke there. The controller was meant to spring apart, but it totally failed to.
I'm sorry.
This is why you do not work with controllers.
So this is what it looks like taken apart. And we identified the parts on the board, as you generally do with a hardware test. The most key things we found were some external memory and an RF module with a very large blob of epoxy on it, which didn't give us very much to work with. So first thing we did was went and looked at the external memory and see what was on it. We managed to find the firmware, which was excellent because usually for microcontrollers, that sort of thing will be embedded on the flash and there'll be some kind of configuration data on the external memory. Either way, we had a look at this, and while we didn't actually use it for any of the reverse engineering, we found it very interesting to look at what was going on in it. So the first thing we saw was that it was using the full 32-bit ARM instruction set, which is very rare for these kinds of technology. Usually they'll use a reduced instruction set called Thumb, which is a 16-bit instruction set, which is used for higher code density, but the lack of opcodes reduces that down. It can be easily identified by looking at a hex dump compared to ARM code and Thumb code. So this is a dump hex dump of the firmware, and the first thing you'll definitely see is a bunch of E's on the fourth byte of every part of the hex dump. So it's a wonderful thing that the top nibble of every ARM opcode defines the conditional, and the conditional is used to define when this sort of thing runs. Now, for a lot of loading, arithmetic, and that sort of instructions, that will always be an always, which is an uppercase E, or 1110 in binary. And here's some of the conditionals that go along with that. So as you can see, ours was going to be always. And again, more of that. As you can see, it's also little endian, so it's always going to be on the 4th byte rather than the first byte of each 4 byte of the thing. And as you can also see, it's 32-bit aligned, so it's much easier to identify that it is ARM code. For thumb code, it's slightly different. Because it has a much reduced code density, it means that every single bit that's being used is used. So all operations, again, are 16-bit aligned at this point, and there are a number of different opcodes in use. So we have a push, which you would generally find at the front of a compiled function, a pop that you'd generally find at the end of a compiled function, and branch and link, which is often used for branching to different parts of the code, and a BXLR, which you don't see that often, but is a similar kind of opcode. Now, looking in the firmware, you can very easily identify these kinds of operations. So here's some thumb code that actually came from the code for our controller that we reverse engineered. So first, you'll see a BXLR first there, then a block of code, and more blocks of code. Now, while this is very easy to identify in the hex dump, because we didn't know the architecture of the MCU in use, it was very helpful for us to be able to identify what kind of MCU was in use so we could reverse engineer the firmware. It was very easy to identify that we were using the furlarm instruction set because of this. Now, Dave's going to talk about the logic analysis.
Right, so the next step is, that's the firmware dump worked. How can we work out what is on this blob? So first step, let's tack some wires on. So fortunately, because it's on a module, it means that we've got some nice, easy places to put wires. And then we can just stick a logic analyzer, and everybody knows what a logic analyzer is. It basically just checks the voltage at various levels and shows you what they are. So next slide. And this is sort of roughly what we saw, which is very stereotypical of a SPI transmission. We have an enable, which tells you which thing is active, a clock, and you can see base activity on it, and MOSI and MISO, which basically say data in and data out. So we'll zoom in on that a bit. So here we can see the clock signal here. It's not actually a very good clock, if any of those pedantic. You can see the clock bits aren't exactly aligned, and then we have the data. So this one's saying the master send out a message of 42, and this is coming back with a message of 2. So after a bit of messing around, we sort of munged it all together, and we worked out what the basic things are. So in SPI, you'll often have something called registers, which is basically bits that can be written to. So we found a load of commands which would allow us to read from and write to registers, status command, and more importantly, register read and write commands at 45 and 05, which are to write stuff into the tank and back from the tank.
And then we use this information to analyze data being received and sent from the controller to the tank and back. As you can see here, these are all the read commands. So these would be video stream data coming back from the tank to the controller, which we could then use to parse that data and make our own video stream from it, and basically use the tank as a CCTV system, a very shit one. Filtering the read commands allowed us to view all received data. This showed the incrementing value at the start of each frame, which we set, allowing us to see the start and end of data payloads as this data was chunked together into separate frames. We moved this together and basically made it into one contiguous piece of data, so it was a lot easier for us to analyze. Now, at this point, what you would generally do is look at the header of the payload, because that will give us the most relevant information. So you'll see some quite easy data there that will tell you what's going on. However, we wanted to talk about that where if you didn't have this sort of useful information on a video stream, as you often wouldn't, because we were expecting this device to be much harder to hack than it actually was. So if we look further into the data, we're just going to look at it without actually analyzing the header. So you can see that it looks like pretty much random data. This would mean it's either encrypted or compressed in some way. A compressed payload would have some sort of form of non-random data at the start and end of the packet, which would allow you to assess compression tables and that sort of thing. So here you'll see that we found, is the HDMI not working?
No, good enough flicker. That's fine.
As you can see, there's some more understandable contiguous data at the top of the payload that allows you to assess exactly what kind of compressed data is going on. And that correlated with what you found using the proper method to actually assess this. If the data was encrypted, the approaches we would have taken were to assess the firmware itself, searching the firmware for information such as that was relevant to the packet, such as a standard size, if it was a standard size, or if we failed at that, we would look at standard constants or tables that are used by encryption algorithms. These could be things like AES boxes or constants used by things like TEA encryption, which would give us a much better idea of what's actually going on encryption-wise. And if we failed that, you could find every XOR instruction, check if there's any compares afterwards, and if there's a jump instruction back to a further part in the subroutine, allowing you to assess whether it's looping through for some kind of stream cipher. We can see you running away, Steve.
Right, that's the boring bit through, honest. That's basically how we went about it, went through all the analysis of it. This is basically the whole bit of this thing that I did. Everything else was Chris. So we found the header, we analyzed the header, and we can see that basically there's the size of the payload, CRC, and the number of blocks in the payload. And finally, the bit that I got really excited about, I used to do forensics work, and FFDF, D8, FF, FE is so obviously a JPEG. It's nothing to do with the amount of porn I searched. So this was highly obvious that this was a JPEG, which generally indicates that it was using something called MJPEG, which is basically a video stream made up of lots and lots of individual JPEG files that it just plays one after the other, which makes it very easy to reverse engineer.
Yeah, so using MJPEG is a very novel idea for an embedded device. Usually you'd use some kind of proper transport stream. And the reason for that is because most of the pictures were corrupted. It had a CRC at the top that meant that a huge amount of the packets that were in use would be just dropped and not shown to the screen because it could have caused memory issues or some kind of corruption. It was a very small size picture, 240 by 180. The device itself advertises a 720p camera, I believe, which can record on the SD card on the device, but that's not very helpful when you have this lower frame rate and the amount of delay, which is about a second when you're using it. Here are some pictures we pulled off the tank at the time.
So,
yep.
Just go back.
Yes, we did want to discuss what we thought about this particular media transport solution.
So this is obviously corrupted because, basically I'm just going to do a live presentation of exactly how this method works for transporting. Here is, I'm not a very good artist, a picture of all you lot watching us, okay? This is how it's going to transfer the data, okay? This is highly effective. Chris, you ready to catch?
Yeah. And I missed it. And because of this, you couldn't put everything back together again. If you had torn it up and thrown it in a few pieces at a time, it'd be much more accurate. But if you drop at least one packet, you're not going to get the image back in a usable format, and that CRC will never match. So trying to transport a JPEG over this kind of format with no kind of retransmission or anything involved is not going to work. For you networking guys, it's like trying to do a TCP stream over UDP, essentially. So here are some images we pulled off. That's part of our office. This is my lovely cat, Momo. And now we're going to talk about the controls. So when we looked at the received data, it was a lot more complex than the controls. The controls are very simple because each frame was one packet at a time. So as you can see, the controls are made up of two analog values, with hex 80 as the neutral value, and then bits set for the controls on the tank. So there were ones for shooting and aiming upwards and downwards and turning and recording on the thing. Whereas the analog controls, we originally thought would be related to the two analog sticks on the controller, which we can show.
No, that controller's not complete. Hold
on. What they actually related to was setting off the speed of the tank treads on the tank. And we also found the controller never put that to full blast. So we found the two analog controls. The tanks rapidly changes the speed of the wheels. We found that the tank itself, if you change the speed too quickly, it would crash and just not work. So if you went forward very quickly and then back again, the tank would just stop and never speak to you again. We also found that the tank was in complete control of when it received controls. So as it was streaming data out, every 22nd frame, it would set a bit on its response and tell you to send the controls.
Just to note, that crash was very, very irritating when we were trying to do videos for this.
So as we noted, the hex 80 basically defined neutral speed, which is often the case. Reverse was a hex 30, which meant a lower value than neutral. A D0 was forward, and FF is what we set it to test it out, which meant we could give it the ability to do wheelies across the room and then make it fall over. The next approach was to find what module was in use on this controller. As we said before, it was using an epoxy blob, so it's very difficult for us to assess what was going on it without starting to burn the thing. So the first thing we did was buy a load of modules, try each module, get angry and destroy the modules, and then profit. So Dave wants to talk about this one.
So while trying to research this, most of these modules came from dodgy vendors in China. And we know how long those take. So I did some sniffing around, and I found this little device from a UK eBay seller, which is basically a generic controller for remote control vehicles, which basically has the 4 major random RF 2.4 gig modules in there. We had a look through, we tried to find through all the data sheets. Data sheets are really the most exciting things in the world. Don't read them. They tell you a lot of information, but they're really, really dull. And we found that the A7105 was the closest match of these. As it turned out, we actually didn't use this at all. It's just, I've got a couple of these just sat at home doing nothing.
So as we found this module, we decided to start buying a few and replaying the SPI commands that we found on the controller so that we could see if we could completely replicate the controls and control it. We used the A7105 that we found and found that while it was very similar to the chips we were working with, it wasn't quite the same. So as we looked through, we found that the data sheets for the A7105 and its brothers in the series, because the company Amicom that released it have quite a few different ones available, they're all pretty much the same, copied and pasted apart from very, very, very small differences, such as the length of IDs or the speed that it can run at, but almost all of them are 2.4 gig modules. Because of this, we thought that finding a transceiver would be very difficult, as the company wouldn't allow us to have any of the ones that they only release to people manufacturing electronics. So we ripped the one off the controller we had. So we basically took the controller we'd taken apart, and I got very drunk, and instead of desoldering it carefully so I could use it again, I took it off and took most of the copper with it, and then cut that off. And then we made a very nice...
never going to work again.
A very nice little shield for it so that we could just control the SPI directly.
Just out of interest, by the way, that's held onto the board with blue tack. That's exactly how technological advanced we are.
So when we were looking at what to use to connect this controller to, we thought either taking a Raspberry Pi, which obviously a very common piece of technology, or using something with a bit of a tighter control on timings, an STM32 development board. Now, these are very common boards to find for development, and they're also, the chips on them are found everywhere in IoT technology. So learning about how to program them is a very important thing to do if you're going to do hardware hacking. We tested the Raspberry Pi, and the timing was just completely off. We couldn't keep up because of Linux, and we didn't want to go completely bare metal for this approach. Instead, we used the ST Nucleo L4967Z development board because it was fast enough, had precise timings, and a USB port, meaning that we could use the STM Cube, a very valuable piece of software that allows you to choose exactly what the pins on the board are doing at a time. So with this, we made a USB device capable of controlling the Nerf tank and streaming the video back to the controller. What we did was we replaced the initial SPI commands that we found on the controller for setting and reading registers, exactly as they were on the board. And then when we found the parts that were reading and writing data, we decided to just copy those into code chunks that we could loop through and then pull the data together. We found the module was very interesting as it starts off in half duplex SPI mode, meaning it uses one pin for sending and receiving data. And then with the register settings, that gets pulled up to full duplex. This is very cool, but makes it very difficult to write initialization code for any of the SPI on it, and HAL libraries just don't work with it. We found that this was very useful, and we managed to use the whole thing to download the data using SPI, stitch the images together, and check the CRC, and then send it over USB back to our host computer. And then we decided to put it on the internet. And here, now
Sorry, we lied about that. The next step wasn't the browser. We tried fuzzing it, because everybody says, why don't you fuzz things? Because you can get interesting results with fuzzing. We're not going to do this live, because it will basically break the tank. Here's a little video I did earlier.
So it crashed at that point and
Yep.
never worked for quite some time.
There was meant to be a shot that came out of that. I didn't see it, but
The speed wasn't too good.
I've got a really bad viewing angle.
Now we had a working controller, we decided to do our next plan.
So if we go back to what we remember, our whole point of doing this was to get a tank, drive it around, and shoot somebody who's currently standing in the middle of the audience. Wave, Steve.
He's there.
Thing is, it's not really efficient to drive it, especially when there's interference. So what we decided to do was attempt some form of machine learning to automatically recognize it. There he's trying to sneak away. So we're going to a section called target acquisition. So I don't have a Steve Lord at home, but in the office we have loads of IoT toys and a color printer. So this is our secret testing facility in a warehouse near Milton Keynes, which we can no longer access because I'd lost the keys. And we just decided to set up a little shooting range. So the next one, and that's our target. Are you feeling persecuted here, Steve? You can't hide behind somebody. And here's a demonstration of our advanced machine learning algorithm by video.
And now we're going to do a demo with the live thing and shoot Steve. I hope you're looking forward to this.
Hold on. We need to.
How can you put it down on the phone?
It's not very good at stairs. It's a bit like a Dalek.
Have you turned it on?
Oh. The on button is very important when testing hardware. Don't worry, I'm fine.
Is it on?
Yeah.
Good.
Now it's not going to work, obviously.
This is the problem with demos, of course. But it does work. And just so you can all get the video stream, which didn't show up for some reason.
The video stream won't work so well because of the interference.
The more of you who turn your phones off the Wi-Fi and Bluetooth, the better this signal will get. Just so.
Somebody rugby tackle him.
We could, of course, do it the harder way.
Have you actually loaded that?
Yeah. Oh. You can't run away.
You cannot escape. It will be in your nightmares.
So, go grab it, hold on your shoulder.
There's an easy cheat to this. Have you ever seen Predator? Oh! I nearly fell over then.
And there's our demo, so thank you very much for having us. Hope you enjoyed it.